Alright YouTube, here we've got an unbalanced Wheatstone bridge, and in this problem we're going to solve for the voltage difference, or the potential difference between these two sides of the bridge. Now there's a couple of different methods for solving for the voltage across this bridge here, but what I want to do today is show you just a real simple way to use basic Ohms Law and circuit reduction in order to come up with the difference in voltage across this bridge. So we're going to reduce this circuit down to an equivalent resistor, just like you've probably done before. And the first thing we need to recognize in reducing this circuit is that this voltmeter or galvanometer is actually an open circuit. It doesn't allow charge to flow from one side of the voltmeter to the other. It's like an open switch. So really, if we were to redraw this circuit, we could simply leave out this voltmeter. See, these two circuits are exactly the same. The only difference is that in this situation where we're calling it a Wheatstone bridge, we've simply run the voltmeter as a bridge across what are effectively the 2 points or 2 arms from here to here. Now the nice thing here is because we have the actual values for the resistance, we can take this entire circuit and reduce it down just like we normally would looking at series and parallel combinations. So first you'll notice these two resistors are in series, as are these two resistors, which means this circuit will reduce down to this, a simple parallel circuit, which we can reduce farther down to this, a simple circuit with the equivalent resistance of our original Wheatstone bridge. So now that we have this equivalent circuit, we can start to work backwards this way in order to solve for the voltage across each individual resistor, which will allow us to solve for the voltage across this bridge right here. So knowing these two resistors are in parallel, we know the voltage across each of them is the potential or voltage across the battery. So solving for the current through this resistor, we find there's 2.25 amps passing through this resistor on the left side of this circuit. Well, that's the same as the current which is passing through the left side of this circuit over here. And we're going to need that in just a second. But first let's look at the current passing through the right side of this circuit. Going back over here, we've got 9 volts across this 6 ohm resistor. And we find there's 1.5 amps passing through the right side of this circuit. Now going back to our Wheatstone bridge, you'll remember these two circuits are completely identical, save this voltmeter or galvanometer right here. So what that means is there's 2.25 amps of current around the left side of this Wheatstone bridge, and 1.5 amps of current around the right side. Now if you've looked at other Wheatstone bridges, you might be thinking, oh wait, doesn't some of the current pass through this bridge? The answer is no. Remember, a voltmeter has infinite or near infinite resistance. It doesn't allow any current to pass through that voltmeter. So ultimately, any current coming down through this wire is going to have to move out through this wire. We don't have to worry about anything like the junction rule right here. So now that we know the current through the left and the right sides, we can use Ohm's Law to solve for the voltage across each of these resistors. So starting with our 1 ohm resistor, the voltage across the 1 ohm resistor is going to be given by the current, that's 2.25, multiplied by the resistance, that's 1. And we find there's 2.25 volts of potential used up in going across this 1 ohm resistor. Looking at this 2 ohm resistor, there's 1.5 amps passing through the 2 ohm resistor. And we find there's 3 volts of potential used up across that resistor. So now we're at the point where we can solve for the voltage reading between these 2 points. And now we have enough information to directly solve for the voltage reading across this bridge. You see, if we look at potential, we know there's 9 volts coming out of the battery, which means at this point right here, there's going to be 9 volts of potential, regardless of which way the current goes. But in going this way through the 1 ohm resistor, the charge is going to lose 2.25 volts, meaning the potential at this point right here is 6.75 volts. Whereas if current or charge passes through this 2 ohm resistor, it's going to lose 3 volts, meaning right here there's going to be a potential of just 6 volts. Now our voltmeter is simply reading the difference in potentials across this bridge. That is to say, it's looking at the difference between 6.75 and 6 volts. And there it is. Using just Ohm's Law and some good old-fashioned circuit reduction, we've been able to solve for the potential across this Wheatstone bridge. Now realize, this method only works if we know the values of the resistors. If we have an unknown value, or we're given all these values as variables, well, then we need to come up with a more general equation using a completely different method. So if you want to see that, stick around and I'll show you how to solve a Wheatstone bridge when we're just dealing with variables. But on that note, that's all for now.